Hi, I'm Stace Maples, and first I want to thank CDL for inviting me to speak about my favorite topic on Earth, which is cartographic information. Specifically, today I'm going to talk about how we make sense of the massive amounts of cartographic information and Earth observation data that are now at our disposal and literally only keystrokes away from a computer. My mission at Stanford University is to support and encourage the use of geospatial data and resources in research and teaching, whatever that means at any given time. And it's a moving target all the time. And increasingly, that means working with massive amounts of pixels. And just very quickly, this is why it matters. Everything is somewhere, and that somewhere does matter. We have to make sense of cartographic information if we want to make sense of the world. So right now, in Earth observation, we are experiencing an explosion in the availability of satellite imagery of the surface of the Earth. And specifically, what that involves is an increase in the cadence, the periodicity with which we can observe things on the surface of the Earth, but also the resolution, both spatial and spectral, that we can observe things on the surface of the Earth. And just to give you an example of the kinds of platforms that we're talking about, Planet.com is one of the companies that Stanford has actually had a very long-term relationship with. And Planet makes available a product called PlanetScope. PlanetScope is made up of a series of 250 tiny satellites that are imaging the Earth on a polar orbit. And as the Earth rotates underneath that polar orbit, that constellation of satellites is line scanning the Earth and giving us an image of the entire Earth every day with 3-meter pixels. Not only that, it's giving us spectral resolution with 8 bands of spectral information that can really reveal things that are not available with the naked eye. In addition to that basic offering, Planet is launching this year 2 new constellations, the Pelican constellation, which will provide 20 to 30 centimeter resolution imagery and the ability to move a satellite anytime you want and take an image of the Earth anywhere you want at very high resolution in near real time with revisit rates of up to 10 times a day. Tanager is their hyperspectral satellite. And what that satellite's going to provide you with the ability to do is move a satellite and take an image that has so many bands of spectral information that you can actually get at material level identification of targets on the ground. This is just a sampling of some of the commercial satellite companies that are now producing satellite imagery on a constant basis that is programmatically, computationally accessible through nothing more than a Python notebook. And the effect of this explosion in these companies is that over the next 5 to 6 years, we're going to see an explosion from 900 Earth observation satellites to more than 2,300 Earth observation satellites. And that represents as much as 230 petabytes of satellite imagery per day. Add to that drone imaging, which in some cases in a single mission can outstrip the size and scale of satellite imagery because of its fine resolution. Drone imaging provides us with sub-centimeter spatial resolution, ultra-high on-demand, specialized and event-driven cadences, and that imagery is it's not possible to process that amount of imagery just with human effort. So how do we do that? Now I want to talk about Earth observation data infrastructures and how we make sense of the massive amounts of satellite imagery that are at our disposal now. 10 years ago, when I first came to Stanford, the way we scaled the analysis of this imagery and the examination of this imagery was with massive screens like you see in the slide right now. This is an HD screen with 35 HD screens on it, and at a 50 centimeter resolution, I can look at over 30 square kilometers of satellite imagery at full resolution on these screens. But that's still not the scale that we need. And this is the problem. Stanford used more imagery from Planet.com alone than NASA last year. That's a massive amount of imagery, and the only way to make sense of that amount of imagery is using artificial intelligence and massive parallelization. So what are the technologies that allow us to drink from the fire hose of Earth observation data that we currently have? What we have now is a data deluge, millions of satellite scenes a day and billions of drone pixels coming in from various sources, hyperspectral and multispectral streams, and all of this requires massive parallelization just to process, but to gain insight, it requires artificial intelligence. And here's the big problem. We collect so much data that until just recently, only 4% of the largest archive, the most longitudinal archive that we have access to, the Landsat project, had ever been examined in any way, just because of the sheer scale of the collections. Well, in the early 2000s, there was a book called The Fourth Paradigm that laid out a path towards managing the scale of the problems, both that we had with the data that we wanted to work with, but the questions that we wanted to ask. And this is a great quote that really encapsulates what modern geospatial and Earth observation technologies are founded on. Often it turns out to be more efficient to move the question than to move the data. And that is more possible than ever today because of data centers like what you see in the background of this slide. Now we can store, for instance, in Google Earth Engine, hundreds of petabytes of analysis-ready data. We can make use of the tiling schemes that back in the early 2000s made web mapping much more efficient. We can use those same types of structures to parallelize the processing of this data. So back in 2010, the Google developers had a problem. They had a map product, Google Maps, online. But the satellite imagery that was feeding that map had clouds in it. This is the southern coast of Borneo that you see here, and it's always got clouds. The nice thing about clouds is, though, they move. And so if you wait a few days or a few weeks and take another image, your clouds are going to be in a different place. And the Google developers, being the innovators that they are, figured out that if you stacked those images up and you looked down through each pixel location, you could find the best pixels for that period of time, and you could create what is effectively a cloud and shadow-free image for base maps. Now, that was just to create their base map product for Google Maps. But they very quickly realized that if you could do that for a year's worth of imagery and compress all of that information into a single image, well, it was just a short step to do something like this, where you take all 40 years at that time of the Landsat archive, turn it into video frames, and suddenly you can see dynamics on the surface of the Earth like you were never able to see them before. And out of that project came a platform called Google Earth Engine. In 2003, we held the first Google Earth Engine conference at Yale University, and I watched David Tao bring up all of North America's Landsat imagery from an entire year and composite that imagery in the same way they had done to get rid of clouds in their base map in a browser in about 10 seconds. Now, when I started doing remote sensing, processing a single image would take hours, sometimes days, just to get ready to do what you wanted to do with it, even to visualize it. And now what we had seen was someone take tens of thousands of images and compress them in seconds into a single image that was interpretable. So why is AI essential if we can do that with data? Well, what I was talking about before is traditional remote sensing. And traditional remote sensing is the processing of pixels, but you still have to make meaning out of that. And that's where AI comes in and becomes really handy. AI allows you to automate feature detection and text recognition and semantic segmentation and look at temporal change over time. Currently, over the past 10 years or so, we've been using machine learning models for the most part to process imagery, but they're very, very expensive in terms of HR, training data, time, and investment. AI has been getting cheaper and cheaper and cheaper to apply to Earth observation data, and in fact, at this point, we're in a world where we have things called foundation models. Foundation models are artificial intelligence models that have been trained on massive amounts of satellite imagery. And in particular, these foundation models are capable of characterizing small chips of visual information and creating numeric characterizations that can be searched for similarity. That is, you can look at a particular feature on the surface of the Earth, and then you can provide that to a database of embeddings, what are called embeddings, and then you can find all of the things in the world, actually, that look just like that. And not just look like that, but have the same spectral characteristics, spatial characteristics, and in some cases, you'll see temporal characteristics. So what the heck are embeddings? I never assume people know what I'm talking about when I talk about embeddings. And I'm going to use a really terrible metaphor, which is food, to explain what embeddings are. So let's say you've got a collection of foods and you want to characterize those foods. Now, each of the axes on this particular slide represent a characteristic of these particular foods. On one axis, you have the dessertness of the foods, and you can numerically quantify that, right? And then on the other axis, you have the sandwichness of each of these foods, and you can numerically quantify that as well. And you can go on and on and on. And in fact, usually what we're doing is we're training these models and we're pulling out thousands of these embeddings values. We're pulling out thousands of dimensions of information, of characterization of these particular images that we're interested in. And these are a byproduct, actually, of the traditional neural networks that we've been using to model and analyze imagery over the last 5 years or so. So now I want to shift and talk a little bit about how you can actually make use of these things in intractable ways. One of the most exciting things that's come down the pike in the last 10 years that I think is the implementation of what's called the Alpha Earth Embeddings database in Google Earth Engine. Google Earth Engine had already revolutionized remote sensing in 2010. Now they're revolutionizing the access to artificial intelligence. So what the Alpha Earth Embeddings are, Google sells them as a sort of virtual satellite, but that seems a little trite to me. What they actually are data that has been collected, a sparse data set, and looped. So you're training on cyclical data. All of the training data that was used in the Alpha Earth model includes satellite imagery that is visual, spectral data. It includes climate data. It even includes Wikipedia articles that have been geotagged. So you have temporal context. You have all kinds of information. And that sparse collection of data is then modeled into a continuous collection of data. And not only that, each of the snapshots in time is informed by a period of time before it, as well as its spatial context. And so in order to grab the spatial context, each 10-meter pixel in this database is using the pixels around it to inform its embeddings. But also, the way that Google is processing this data and training this model, they're using a video model to do this. And so they're running this through as temporal data as well. So you have both the spatial and the temporal context. And what that means is that every pixel in this database knows its history and its neighbors. The really brilliant thing that Google has done with this embeddings database is to model it and store it in a way and make it accessible in a way that feels natural to the people who would be using it, and that's remote sensing analysts. They've taken this database and they've modeled it as bands in a global image that you can access within the Google Earth Engine platform just as you would any remote sensing data. Now, if you want to roll your own embeddings, perhaps you have your own data that you want to process and calculate your own embeddings, the Clay Foundation model, I think, is one of the most promising models to come along, and that's because it's really sensor agnostic. It's one of the first foundation models that's not tied to a specific data source. It works with optical, multispectral, hyperspectral, synthetic aperture radar, and because the configuration of your sensor is just a configuration file that you give to the model to tell it what the spectral and spatial characteristics are, you can feed it anything, and it can create embeddings on that data. And what that means is whereas traditionally in the past, if you were using artificial intelligence to process imagery, you had to have a separate processing stream for every data source that you wanted to work with. But now with the Clay model, you have a single model that you can pass all of your data through, and you can get all kinds of results out of that. Now for something not completely different, but slightly different, historical maps present a scaling problem too. And that's because there are so many historic cartographic resources now available digitally through platforms like IIIF, the International Image Interoperability Framework. The U.S. Library of Congress alone holds 5.5 million maps, many of which are available at IIIF endpoints. The David Rumsey Map Center at Stanford University, we have 150,000 maps available across the API, the IIIF API. And there are currently hundreds of institutions using IIIF. That means there are potentially millions and millions, possibly billions, of maps available for people to work with computationally. That again presents a scaling problem because what we're interested in is not the maps themselves, but the information in those maps. And so Stanford has worked over the last few years with several projects to create infrastructures for extracting cartographic information from those paper maps and making it computationally accessible. One of the first experiments was a project between David Rumsey and the Knowledge Computing Lab at the University of Minnesota, and that's the Map Curator. This was a pipeline that was able to extract text in a meaningful way from cartographic information, from scanned historic maps, and place it in a geographic framework so it could be used as actionable geographic data. And it did that not by treating maps as maps, but treating maps as background to text. And so the model was actually trained on random images with typography superimposed on them. And this turned out to be a really elegant way to teach a model to see the text on a map. Whoop. MapReader is the next generation of that Map Curator product, and it can do semantic identification of the features in the image chips as well as the text extraction. All of this data is then stored as GeoJSON, which is immediately actionable in a computational environment. So why do historic maps still matter? Well, in a conflict situation, authoritarian regimes often try to control narrative by manipulating geography. They alter maps, they rename places, and they delete settlements. But historical maps, especially those held in independent archives, reveal those attempts at manipulation by providing fixed points of reference and comparison. This creates what you might call a cartographic chain of custody. Every edition of a map is a timestamp. Every place name preserved is a record of cultural presence, and every change in naming or boundaries reflects political intent. The human capital that makes this possible are the archivists and cartographers, historians, the local knowledge keepers, and the technologists who are the stewards of this cultural memory. Maps preserve truths of memory. Earth observation preserves reality, and artificial intelligence provides understanding at scale. And I want to leave you with this one last thought. Human capital in mapping is not just about technical skill, it's about safeguarding the memory of landscape. In war, occupiers often try to erase cultures by erasing their place names. Historical maps protect the truth of who lived where, what communities built, and what was destroyed. They become tools of accountability, restitution, and recovery long after a conflict ends. Thanks.
Thank you, Stace, for this fantastic presentation. I can assure you that, particularly the last point about, the cultural and historic legacy that is carried by the archivists and people who work on those issues, is very telling to this country being occupied for 50 years by the Soviets. I mean, clearly we understand a fair deal about what it means if a map is obscured and the names and the topography is actually changed. So I'd be very, very interested in demonstrating what this country has done now within the modern days to digitize its own geospatial kind of archives. But we have time for a few questions. And if I may, with all things considered, with the hardware that is now flying around in the orbits, and the machine learning, and now with the AI applications actually making insights based on those data, is our privacy disappearing?
It's a fantastic question. I work with the school with public health projects a great deal. I think the answer is probably yes. To some degree, these technologies are able to peer into private spaces, backyards. I mean, the resolution of these satellites is unprecedented. We're now talking about satellites that have as high resolution as 20 centimeter pixels, and that is enough to identify cars and things of that sort, count people even in crowds, and so yes, there are concerns about that. Combine that with the fact that these technologies are very nearly real time now. And they can be merged. They can be fused with other data streams. For instance, mobile data. So if you have video imagery, drone imagery of the dynamics in a neighborhood, if you also have the contemporaneous information about people moving around in those places, mobile data and things of that sort, then you can really gain personal insights into people. So you do have to be careful about these types of satellite systems. The one caveat I would say is that that kind of monitoring is not yet ubiquitously possible. And the reason for that is bandwidth, right? These platforms that are getting higher and higher resolution and more bands of information, well, there's a trade-off there. You can't monitor constantly with those platforms because we simply can't bring the data down fast enough. And in fact, most of those platforms aren't even going to bring raw data down. What's going to happen is we're going to have AI agents on the satellites themselves pre-processing data into insights, and those are the things that are going to be shipped down terrestrially for our use, the actual insights themselves.
So likely the benefits will outweigh the challenges that you would face with
I hope so.
privacy. Because I mean, this is an argument that I clearly like. I mean, if you were to be concerned about the privacy, then that effectively stops your innovation.
Sure.
In this part of the world, the deterrence, resilience, and the defense is something that brings an extra layer, because what we tend to do with our satellite imagery, remote sensing data, this is largely in public domain. And that is equally available to us as much as the adversary.
Same for us.
Exactly.
Landsat and Sentinel are public domain.
So wouldn't you agree that we need to rather live with this new reality and learn how to not maybe so much protect ourselves, which definitely is worth to explore in its own right, but to actually make better AI models, make better ML models, to get a strategic advantage ahead of the adversary.
Yeah. I think what we have to do is create a sense of integrity in how we use these resources and not be bound by adversaries' use of the resources, right? We need to maintain that sense of integrity in the use of these resources. Yes, we need to innovate faster so that we can stay ahead of adversaries. But like you've observed, these technologies are ubiquitously available. You can go and get a free Google Earth Engine account right now. All you need is a Gmail, and it's totally free to access all of this public domain data. And so yes, this is a concern, but I think the benefits far outweigh the risks. In the same way that telecommunications can be used nefariously, but we don't throw that technology away because on balance, they provide more positive benefits to humanity than negative benefits.
And on a final note, Stace, if you would highlight just one facet of this innovation that we see in satellite imagery, remote sensing, what is the most practical impact from an individual perspective?
The most practical impact from an individual perspective is that we can now turn these massive amounts of satellite imagery into real actionable information for decision makers who are going to make the world easier to live in for us. They're going to, these technologies, because we can now monitor ubiquitously, allow us to not only see that deforestation has happened somewhere, but see that it happened today and go and stop it. We can, one of the projects that I work on is a human trafficking project, and what we target is charcoaling operations in Brazil. They tend to be associated with human trafficking. So we are monitoring Brazil right now, looking for deforestation, and then these patterns that indicate that charcoaling has begun, and interventions happen then, and interventions that free people from human bondage.
Thanks. I love the example on the real timeness of the impact, because in this country we're trying to build systems where we can really monitor and calculate. For example, the real-time observation of carbon dioxide sequestering by forests, and these are the kinds of the examples that will actually drive forward the innovation. So maybe we shouldn't be concerned so much about protecting everything, but actually thinking about where we can release new value. Ladies and gentlemen, this was Stace Maples, Assistant Director of Geospatial Collections and Services at Stanford Libraries. Thank you very much.
Thank you.